Hello, we are starting our discussion on an algorithm for solving the transshipment problem. The algorithm is called network simplex, which, as you can tell, is derived from the simplex algorithm for linear programs. We will take the simplex algorithm and see what happens when we apply it to the LP for the transshipment problem. We can then translate that to an algorithm which we will apply directly to the diagrams of the transshipment problem instead of doing calculations on matrices. We start by recalling that in simplex, we are required to have a basic feasible solution, and the algorithm will move from one basic feasible solution to another basic feasible solution. So in this lecture, we will discuss what a basic feasible solution looks like for the LP for the transshipment problem. First, let's recall what is a basis. Here's an example of an LP. Now, a basis consists of a set of linearly independent columns that form a square invertible matrix. And just as a technical note, a basis could refer to these columns or the variables representing these columns. In this example, the columns 1 and 2 are independent and they form an invertible square matrix, so that is a basis. But the columns 2 and 3 are not independent, so they cannot form a basis. The main reason for having a basis is that each basis corresponds to a unique basic solution, which you can obtain by multiplying both sides by the inverse of the matrix and set the non-basic variables to 0. In this example, I multiply my inverse on both sides to get this system, and by setting x3, x4 to 0, I can easily get a basic solution, 2, 1, 0, 0. And this correspondence between the basis and the basic solution is good because I only need to know one to get the other. Once I know the basis, I know what the solution is. Once I know the basic solution, I will know what the basis is. Now let's see how this applies to the LP for the transshipment problem. Here is the example from previous lectures. I have written down the constraints here. I removed the arc costs because they are not relevant here. So let's focus on the incidence matrix that is on the left-hand side. To find the basis, I need to have 5 independent columns because there are 5 rows. Now, spoiler alert, you won't be able to find 5 linearly independent columns in this matrix. So why is that? Let me give you a few seconds to pause and think about it. Now, the reason that you cannot find 5 independent columns is because the rows are linearly dependent. We can easily see that since each column has 1, 1 and 1 minus 1, so by adding all the rows together, we get a 0 vector. So the rank of this matrix is at most 4, so we cannot find 5 linearly independent columns. Does this mean that simplex is dead for us? We cannot even find a basis? Well, the answer is no. We can still continue to apply simplex, but with a small modification. One of the things we always assumed in simplex is that the matrix has full row rank, that is, all the rows are linearly independent. But what if it does not have full row rank? Then we can apply row reduction to the system and get an equivalent system that has full row rank, and then apply simplex. So in this case, the size of the basis is really just equal to the rank of the matrix. For the transshipment problem, we are not actually going to run simplex on the matrix form, so we do not need to worry about row reduction. But we would still like to know what is the rank of the incidence matrix of any digraph. Well, we know that the number of rows is equal to the number of nodes, and the rows are dependent, so the rank is at most the size of n minus 1. So we want to know if we can find this many columns that are independent. Now each column represents an arc, so we could just say which arcs we can pick so that the corresponding columns form a basis. As it turns out, the independence of a set of column vectors in the incidence matrix has a lot to do with cycles in the digraph. Let's look at the following digraph. Consists of just one cycle. Note that this is not a directed cycle. And let's look at the incidence matrix for this cycle. You will notice that the incidence matrix is a square. That's because in a cycle, the number of nodes is equal to the number of arcs. Just like what we discussed before, the rank is at most 3, so the columns here must be linearly dependent. Now suppose this cycle is part of a larger digraph. Then the columns of these arcs in the new incidence matrix would just be these 4 columns except with more zeros padded. So these 4 columns are still dependent. So that means that any set of arcs that contains a cycle would not be independent. So that gives us this following proposition. If a set of arcs contains a cycle, then the columns of the incidence matrix corresponding to these arcs are linearly dependent. So if we have a cycle, then the columns are dependent. But what if we do not have a cycle? Then, as it turns out, these columns must be linearly independent. And that leads to our next proposition. If a set of arcs does not contain the cycle, then the columns of the incidence matrix corresponding to these arcs are linearly independent. The proof here is trickier, and we will provide a sketch of this proof. Let's suppose that the columns of our set of arcs is not independent. Then there must be some non-trivial linear combination that gives the zero vector. We now remove columns with 0 as its coefficient, which leaves us with only columns of non-zero coefficients in this linear combination. Now for each row, we see that either all the entries are 0, or at least 2 entries are non-zero. Can you see why that is? We collect these arcs and the nodes with at least 2 non-zero entries within these columns. Now we have a digraph where every node is incident with at least 2 of these arcs. This digraph then must have a cycle. This is a standard result from graph theory, and you can try to prove this yourself. And this concludes this proof. So to find independent columns, we just need to find arcs that don't form cycles. To find the basis, though, we need to have as many of these arcs as possible. Now, what does that mean for a connected digraph? We want to have no cycles with as many arcs as possible. Well, for connected digraphs, these are precisely the spanning trees. We know that for any connected digraph, a spanning tree exists. And a spanning tree has n-1 arcs, and they will correspond to n-1 independent columns in the incidence matrix. So the rank of the incidence matrix must be at least n-1. But previously we said that the rank is at most n-1, so the rank must be equal to n-1, and we have a basis. So this results in the main theorem for this lecture. Let M be the incidence matrix of a connected digraph D. Then the rank of M is n-1. Moreover, a set of n-1 columns of M is a basis if and only if the n-1 arcs corresponding to these columns form a spanning tree of D. As an exercise, you can try to determine the rank of a disconnected digraph. Now that we know how to find the basis, we want to know how to find the corresponding basic solution. Back in simplex, we can just multiply the inverse of our matrix and set the non-basic variables to 0. But we cannot do it here because we do not have full row rank. However, we can use some linear algebra to show that if a solution exists, then it must be unique. Let's look at it from the transshipment problem point of view. Here's our example from before. Let's draw a spanning tree, which is a basis. The remaining arcs must have zero flow because those are the non-basic variables. If we look at node A, we see that all the arcs around A are determined except for the arc AC. So using the flow constraint, we see that minus xac minus 0 should equal to minus 5. Solving this gives us xac is equal to 5. Next, if we look at the node B, we see that there is only one arc around it that is not determined. Looking at the flow constraints, we have 0 plus xcb plus 0 is equal to the node demand 7. So that tells us that xcb is equal to 7. And next, we look at the node C. We have incoming arcs 5 plus xdc minus the outgoing arcs 7 and 0 is equal to the node demand 0. Solving this gives us xdc is equal to 2. And we can do the same thing for DE. That gives us xDE is equal to 3. Notice that the constraint at node E is not used to determine any of the flow values. That's because that constraint is really redundant. But we can really check quickly that node E is also satisfied. So we have our basic solution here. Now we see that all the flow values are non-negative, so that makes this a feasible solution as well. So in general, what we do to solve for a basic solution is we find a leaf, calculate the flow at that leaf, remove it to get another tree, and we repeat. In the end, if we get a feasible flow, that is, all the non-negativity constraints are satisfied, then it is a basic feasible solution, BFS. Now, is it possible that a basic solution is not feasible? And the answer is yes. So let's consider this tree. It'll be a good exercise for you to come up with a basic solution corresponding to this spanning tree. If we do this according to our method, we see that it will give us a negative flow on the arc AD, so it is not a feasible solution. Now the question of finding a basis solution that is feasible will be discussed in a future lecture. For now, we will just find a basis feasible solution by inspection. In the next lecture, we will see how simplex operates from a primal dual perspective. This will lead us to the network simplex algorithm for the transshipment problem.